Hi class, this is section 4.4 on indeterminate forms and L'Hopital's rule, part 1. Consider the function h of x is equal to the natural log of x divided by x minus 1. The function is not defined at 1, but what about the limit as x goes to 1? In general, if we have a limit of the form, the limit as x goes to a of f of x divided by g of x, in which the limit of the numerator is equal to 0 and the limit of the denominator is equal to 0, then the limit of the ratio may or may not exist. It is called an indeterminate form of the type 0 over 0. Here are some examples that we've already seen. So the limit as x goes to 2 of x squared plus x minus 6 divided by x minus 2. If I plug in a 2 in the numerator, I'll have 4 plus 2, which is 6, minus 6, so 0 over 0. To evaluate the limit, factor and cancel. The limit as x goes to 0 of sine x over x we've seen already, as well as the limit as x goes to 0 of 1 minus cosine x over x. So again, for that first guy, we can factor and cancel, and the limit is equal to 5. For the second two, there are geometric proofs in your textbook. We actually just looked at the graphs, and I said we talk about it later. So we're going to prove these using L'Hopital's rule, but the book does offer a geometric proof. Okay, so those two methods, though, using some kind of geometric proof or factoring and cancel, won't work for the problem that we're looking at. The limit is x goes to 1 of ln of x divided by x minus 1. And then what if we want to take the limit as x goes off to infinity? So the natural log function grows without bound, so the numerator goes off to infinity, as does x minus 1. So this leads us to another type of indeterminate form, infinity over infinity. So again, the limit of the ratio may or may not exist. Okay, and we've seen this before. So let's say, for example, we're taking the limit as x goes to infinity of x squared plus 5 divided by 2x squared minus x plus 1. We can disregard everything except for the leading term in both the numerator and the denominator. Reduce your fraction, and we see that the limit is equal to 1/2. Okay, so L'Hopital's rule will provide us with another method for evaluating the limits that we already know how to evaluate, but then also evaluating the limits that we're not able to factor and cancel or use some other method that we've learned already. Okay, so let's suppose that f and g are differentiable functions and that the derivative of g of x is not equal to 0 on some open interval containing a, except possibly at a itself. All right, so if either the limit as x goes to a of f of x is equal to 0 and the limit as x goes to a of g of x is equal to 0, or we're in the case where those limits are equal to either plus or minus infinity, then the limit as x goes to a of f of x over g of x will equal the limit as x goes to a of f prime of x over g prime of x, as long as this limit on the right-hand side of the equation exists. This will also be true if the limit on the right is equal to infinity or negative infinity. Then that'll be the answer to the limit as x goes to a of f of x over g of x as well. Okay, so these are indeterminate forms of 0 over 0 or infinity over infinity. Okay, so I'm going to provide a short proof of the first case. So if the limit as x goes to a of f of x is 0 and the limit as x goes to a of g of x is equal to 0. Okay, so both of these, numerator and the denominator, are going off to 0. Okay, subtracting 0 from both the top and the bottom isn't going to change anything. Okay, and then since we're assuming that the limit as x goes to a of f of x is equal to 0, here I just have a c instead of a, but the limit as x goes to c of f of c, that would be 0, and the limit as x goes to c of g of c is also equal to 0. So I replaced the zeros with f of c and g of c. Okay. Okay, so next I wanted to divide the numerator and the denominator by x minus c. Okay, so we can now take the limit of the numerator and the denominator separately, and hopefully this will look familiar to you. Once we take the limit of the numerator, the limit is x goes to c of f of x minus f of c over x minus c, right? That was our definition of the derivative. So we have the limit of the top over the limit of the bottom, and again, this is the definition of the derivative at c, so that's our f prime of c. Same thing in the denominator, that's our g prime of c. And then I can just go back to the limit notation. So this is the limit as x goes to c of the derivative of f over the derivative of g. Okay, one thing to notice about L'Hopital's rule, again, show me that it applies, right? So we're either in the case of 0 over 0 or infinity over infinity. Take the derivative of the numerator on its own, take the derivative of the denominator on its own. So we're not using the quotient rule. All right, so let's look at some examples. These are the three that we've already answered, okay? We factored and canceled, but this time we'll try it using L'Hopital's rule. Okay, so what I'm looking for is, first of all, that you show me that L'Hopital's rule applies. So if I plug in a 2 to the top and the bottom, I'll get 0 over 0. Okay, one option is to just write a capital L apostrophe H for L'Hopital's. That way I know what you're doing. So then we have this is equal to the limit as x goes to 2. Take the derivative of the numerator, we'll get 2x plus 1 over the derivative of the denominator, so that's 1. As long as this limit exists, then it'll be our final answer. So now we can just plug in a 2. Okay, so 4 plus 1 or 5. Good. The second one, again, as x goes to 0, the numerator sign of 0 is 0. Also the denominator goes to 0. Tell me that you're using L'Hopital's rule. You need to rewrite the limit because we haven't taken the limit yet. Derivative of sine is cosine. Derivative of the denominator is 1. So now we can just plug in a 0. So cosine of 0 is 1. Okay, good. For the next one, x is now going off to infinity. So the numerator x squared plus 5, that will increase without bound. So that goes off to infinity. Same thing in the denominator because I know it's that the leading term is what influences the entire polynomial. So the denominator will look like 2x squared. So that also goes off to infinity. All right, so now we apply L'Hopital's rule. The derivative of the numerator is 2x. The derivative of the denominator is 4x minus 1. Good. This is still indeterminate. The numerator is still going off to infinity, and the denominator is still going off to infinity. So we can use L'Hopital's rule one more time. This time the derivative of the numerator is 2, and the derivative of the denominator is 4. So we take the limit and we'll get 2/4, which reduces to 1/2. Okay, good. So sometimes L'Hopital's rule will be faster. I think, especially if we call this guy part C, it was easier doing it the other way, I think, where you just disregard everything except for the leading terms. Okay, but both methods work. Okay, so now these are the ones that we were not able to evaluate before. So again, as x goes to 1, I'll have the natural log of 1, which is 0. The denominator 1 minus 1 is 0. Okay, so I've shown that L'Hopital's rule applies. L8, so I'm telling the reader that I'm applying L'Hopital's rule right here. So this is the limit as x goes to 1. Take the derivative of the top, so that's 1 over x. The derivative of the bottom is just 1. So now when we take the limit as x goes to 1, we just get 1. All right, and now the limit as x goes to infinity of the natural log of x. That is going to increase without bound, as does x minus 1. So this is the limit as x goes to infinity. The derivative of the derivative of ln of x is 1 over x. Derivative of the denominator is 1. So now x is going off to infinity, so I have 1 over a very large number, so this limit will equal 0. Example 2, part A. So now we have the limit as x goes to 0, tangent x minus x divided by x cubed. Okay, so if I just plug in a 0, tangent of 0 is 0 minus 0 over 0 cubed. So we have 0 divided by 0. Therefore, L'Hopital's rule applies. Let's take the derivative of tangent, so that's secant squared, minus the derivative of x, so minus 1. And then in the denominator, take the derivative, and we will have 3x squared. Okay, so let's see if this is better than what we started with. So tangent, our trig function, increased in power, so that's not good. But the other two, the x and the x cubed, were polynomials, so those decreased in power, which is, tends to be more simplified. So it's kind of a mix, but it certainly didn't get worse. Okay, so now let's see what happens if we just take the limit. So we'll plug in 0. Secant, if you remember, secant x is equivalent to 1 over cosine of x. So when we plug in 0, since cosine of 0 is 1, secant of 0 is also equal to 1. So square it, and we'll be at 1, but I have a minus 1 in the numerator. The denominator goes to 0, so 0 over 0. So it's still indeterminate, but let's apply L'Hopital's rule a second time and see what happens. Okay, so the derivative of secant squared, bring the 2 out front, times secant, now times the derivative of the inner function, so that is secant x tangent x. The derivative of 1 is just 0, so that goes away, and then we'd have 6x in the denominator. Okay, so we have the limit as x goes to 0. We can reduce our fraction, so just a 1/3. So in the numerator, we have secant squared x times tangent x. In the denominator, 3x. Okay, if I plug in a 0, secant squared is going to go to 1. Tangent goes to 0, so I have 1 times 0, or 0 in the numerator. The denominator goes to 0. So I again have 0 over 0. Okay, and I don't want to take the derivative of the numerator again, because now I'll have a combination of the product rule and also the chain rule. So I can tell that taking the derivative another time will make the numerator a bit of a mess. Okay, so let's just figure out what's causing the problem and which portion of the limit is actually okay. Right, so the secant squared is not causing a problem, and neither is the 3 in the denominator. So the 1/3 can even be pulled out. So we have 1/3 times the limit as x goes to 0 of secant squared x, and then let's multiply this by the limit as x goes to 0 of tangent x over x. Okay, so the reason we know that the limit of the product is the product of the limit as long as the limits exist, so we still have to confirm that second part. Okay, this first guy is just going to go to 1, so that's good. So as long as the limit of the second one exists, then we're able to do this step. Okay, so limit as x goes to 0 of tangent x over x. This was what was causing the problem, since tangent of 0 is 0, and obviously we have a 0 in the denominator. So I'm going to apply L'Hopital's rule just for this limit, just for this guy right here. Okay, so we have the limit as x goes to 0. Derivative of tangent is secant squared. Derivative of x is 1. Now we're good plugging in 0. Secant of 0 is 1 squared, and we still get 1. Good, so let's go back up a line. I have that 1/3 out front, times 1, so final answer will be 1/3. Okay, this is one option of how to evaluate the limit. With this guy that I have circled, you could have rewritten tangent as sine over cosine, and then we know that the limit as x goes to 0 of sine x over x is equal to 1, or you could have applied L'Hopital's rule to the sine x over x as well. Okay, so a few different options. Either way, you should get 1/3 as your final answer. Okay, so example 2, part B, evaluate the limit. So you'll complete this and turn it in through Canvas. We're taking the limit as x goes to infinity of the natural log of x divided by rad x. Okay, good luck. Let me know if you have any questions.